Hello and welcome to this video, which is part of the Introduction to Machine Learning for Engineers class. So today what we are going to do is to see how to use in practice, how to put in practice the previous lesson that we saw. So in the previous lecture, what we saw is an introduction to the first supervised machine learning algorithm, which is in this case was linear regression and polynomial regression. And today we are going to see how to use it in practice in Matlab in order to build a first regression model and to be able to use it to make some predictions. So for this, the example that we are going to use for this case is we are going to try to look at the evolution of the population of China over the years. And the ultimate goal will be able to try to make a prediction of what the population of China will be in a few years from now. So the different things that we are going to use and we are going to see in this lecture is first how to use Matlab in order to build a polynomial regression model. We are going to see how it's important to rescale the features in order to make the regression model, the training of the regression model more efficient. Then we are going to see how to optimize the model. In this case, we are going to see how to optimize the complexity of the model, which in this case depends on the polynomial degree. So we are going to see how to choose, how to pick the best polynomial degree for the model, which will allow us to find a model that is not underfitted and not overfitted. And then we are going to see how we can validate this model by using by splitting the data into a training and validation set. And then once we have a model, we will use it to make some predictions. So the first thing, of course, we'll be able to, we will try to load some data. So for this, I will just rely on some data which is in an Excel file, so a CSV file. So in this case, what we are going to do is to load the data, which is in this Excel file like this. And so we are going to load it into a matrix. So we are going to read the data and to convert it into a matrix that we later on we can use in Matlab. So this is going to be the first step, which is the importing the data. Of course, this is always the first step in machine learning. You need to have some data. If you don't have any data, then there is nothing that you can do. So now what we have now is some data. So here the data that we have is column 1 is the year. So we have some data starting in 1960 up to 2018. And so we have here 59 different years. And for each of those years, we have the population of China, or at least an estimation of the population of China, which is expressed in millions of inhabitants. We will plot this information in a few seconds to see what it looks like. So now that we have this data, since the first column is going to be the feature, like it's the year, that's going to be the input of our model. So we are going to load it in a vector x. So we are going to say that x we are going to use to use a fraction of the matrix data that we just created. So in this case, the matrix data, if we look at its size, the size of the data matrix that we just created has 59 lines. This is the number of data points, the number of examples that we have. And its horizontal size is 2, which is because you have two columns. One is the input, one is the output. So here what we are going to do is we are going to extract from this matrix X, we are going to take all the lines, but to keep only the first column. We are going to keep only the first column and exclude the second column, and this is what is going to give us our feature X. And then we're going to do the same to extract the observation Y. So we're going to take the data, select all the lines, and only keep column number 2, which is going to give us the feature vector, which contains all the population of China, which is what we want to predict. So then just since it's a variable that is going to be useful, we are going to save in the variable m the length of, for example, variable x. So this is going to give us the number of different training examples that we have, which in this case is 59. Okay, so now that we have imported those data, the first thing that is always useful to do is to be able to visualize those data, have an idea of what is the data by plotting them. Sometimes we cannot do that because the data is can have a lot of dimensions, but in this case it's pretty easy. We have only one dimension, which is x, and the one dimension for the feature and one dimension for the observation. One dimension for x is just a one-dimensional vector, and y is also a one-dimensional vector. So now the second step is we are going to visualize the data, which in this case is easy to do because we have only one dimensions. So the first thing that we do is just to plot y as a function of x. So let's plot it like this. So if we just do this, so what we see is that we have different points here which correspond to an estimation of the population of China as a function of the year. So as you can see here, those are probably not the most accurate data because there's a lot of noise in the data. So here, like, the noise is a little bit exacerbated. Like there should not be so much noise in when you look at the population of a country, but typically in real world data there is a lot of noise, and we need to know how to deal with this noise. So here what we can see is there is a few conclusions that we can just come up with just by looking at the data. We see that obviously the population is growing over time, but it looks like just at first sight that the population, the rate at which the population is growing tend to gradually slow down over time. Like it looks like the slope is slightly decreasing over time. Another thing that is pretty useful to do is to plot some distribution of the features, just to have an idea of the type, the variation of the features that you have. So for this, one thing we can do is to plot a histogram. So we can plot a histogram of, for example, the variable x. So if we do this, so if we choose, for example, we can choose 10 bins. What it will do in this case, what Matlab will do is to take all the values of x and to sort them into 10 different bins, 10 different domains, and to plot the distribution, like the number of samples that you have in each of those domains. So here what we see is that obviously when you look at x, it's a very homogeneous distribution. Like we have data for pretty much all the years, and we have, in this case, it's a very homogeneous variable. We just have the same number of data throughout the entire range of the range of the features. From 1960 up to 2018, we have the same number of data. If we look at now what happens on the for the observation for the value of y, so here it's a little bit different. We have some kind of distribution of the data. We have like a peak of a lot of data towards 1.3 million data points. So which is which is kind of the average population of China, and then we have still a range of measurement around this this average value. So now that we are aware of the relationship between input and output, like just by looking at it, now that we are aware of the distribution of the feature input x and the observation y, now we can start thinking about how to start building a model, a regression model that can predict the population of China as a function of the year. So for this, the first thing that we are going to do, we are going to start with a very simple model. We are going to start with just a linear regression, a pure linear regression. That is to say, we are going to assume that the hypothesis for this model is just that y is going to be a linear function of x. So we are going to assume first that the population of China is a linear function of the year. So something that can be written as a times x, or a times x plus b. So we are going to assume simply a linear model like this, ax plus b or mx plus b. So and let's see what we get. So the good news about Matlab is that you don't have to code yourself the gradient descent training algorithm that we saw in the previous lecture, although that would not be necessarily very difficult to do so. But in this case, we are going to benefit from the built-in function within Matlab, which is going to parameterize a linear regression model for us. So what we are going to see for this is to use the polyfit function. So we are going to use the polyfit function. So what the polyfit does is that it takes 3 arguments. The first thing is going to be the feature vector x. The second argument will be the observation vector y, that is to say the population of China. And then the last argument that you need is the degree, the polynomial degree. So we will start here first with a degree 1. And then what this function will return is the coefficient of the linear regression, that is to say the coefficient a and the coefficient b. So this function is going to return a vector, and the vector is going to be the coefficient. And the first coefficient is always the one that is associated to the higher degree, which in this case is just x. So the first vector will correspond to a. The second vector in this case will correspond to b. So it will give you the coefficient in order of decreasing coefficient. So if you do a second order regression, it's going to give you first the coefficient associated to x2, then the coefficient associated with x, then just the value of the intercept. So it's gonna we need to store this information, so we can store it in a variable p, where p is going to be the list of the coefficients. So in this case, now we have a new vector p, which has 2 coefficients. The first one is the slope of the model. So this is the slope, the coefficient a, and the second one, b, is going to be the intercept. So now that we have this list of coefficients, now we can see how well the model is working. So the way we can do this is now to use what would be the predicted value of y if we use this coefficient. So what we can do now is to say, okay, I'm going to assume that this model works. So I'm going to predict what would be the value of y that would be associated with the features x. So what would be the population of China that is predicted by this model as a function of the year x. So for this, one function that makes it easy to do with Matlab is to use the polyval function. So we are going to use the polyval function here. So what the polyval uses is, first, it takes as the first argument the coefficient p, so the vector of coefficient p that you just obtained from the polyfit function, and then it's going to associate that with the range of features x, and for all of those features x, it's going to calculate the corresponding observation y. So now what we are going to do here is to evaluate the model. We are going to calculate for this model, for all the values of x, what is the predicted population of China. What is the predicted observation y? And then we are going to plot what it looks like. So we are going to, in this case, replot the raw data. So let's replot x as a function of y as a function of x as individual points. Then we are going to use the hold on command in order to be able to plot several plot on top of each other. Then we are going to plot, in addition to that, now the prediction of the model. So now we are going to plot as a function of x the predicted value. So the value that is the y pred vector, which is given by a polyval, which is the vector of the predicted value, the values, the population of China that is predicted if we believe this regression model. So let's see what it looks like. So we are going to plot this, and then we are going to put hold off to say that we are stopping to plot, to add plots on top of each other. So let's see what we get. So now on this plot, what we have is the blue individual points are the actual data within the training set, and this red line are the predicted value. So in this case, since we'd use a regression model, so just with a first degree hypothesis, then we get just a simple red line. And as you can see here, this red line is already doing a pretty good job at representing the data. It's capturing the data pretty well within the noise. So it's already a pretty decent model, but it does not capture the fact that it looks like, when you look at the data, it looks that the slope is gradually decreasing over time, that the population increases over time, but that the rate of increase of the population tends to slow down over time. So just to see what we have obtained so far. So on the variable x is just a column vector that contains the years. So this is the feature vector. On the variable y, this is also a column vector that contains the real observation. So the observation that we use to train our model. We have 59 point here. And then in the y pred, so we have the predicted value, which is what our model is actually predicting. And in this case, we have also 59 value because we are predicting what the model is telling us for each of the 59 features. For each of the 59 years that are used to train the model, we get also its prediction. So one key thing that we need to do now is to see how good this model is. Of course, we can look at it and see that it looks pretty good. But if we want to evaluate the accuracy of the model, we need to calculate the mean square error, or the root mean square error. So for this, it's pretty easy to use in Matlab, because we can do some operation on those columns. So the way we can calculate the mean square error, the MSE, is just to take the difference between the predicted value minus the real value. Then we put this difference to the square. Be careful here. If you just put square like this, what it will do is it will try to make a product between those two columns, and that's going to cause an error because those matrices don't have the right size. So here we want to take the square of each of those elements. We want to define a new column vectors that is the difference between the predicted value of y minus the real value of y, and then for each of the elements of this vector we want to put it to the square. So for this, if we want to do it an element by element square rather than a matrix product where we take this matrix and multiply it by itself, then we need to add a point hat rather than just the hat. So if we do this, we get now we will get a vector. So if let's just see what it looks like. So if we take if we just take the difference between the predicted value of y, we get a new column vector which is sometimes positive, sometimes negative. This is the difference. This is the vector of the residual. The vector of the residual is for each point. It's the difference between the predicted and the true the true value. So if we put it to the square, so if we don't put the point here, this is not going to work because it will think that we want to do a matrix product. So we need to add the point hat like this. Now we have a new vector that corresponds where all the values are positive and where all those values for each of those elements correspond to the square difference between the predicted and the true value. So now that we have this, to get the mean square error, we need to first calculate the mean. So now what it will do is to calculate the sum of all those squared error and divide it by the number of training examples. So it calculates the average. So this is going to give us the MSE. And if you want the RMSE, the root mean square error, then we can just calculate the square root of this thing. And this is going to give us now the RMSE. So let's just see what it looks like. So far we get an RMSE of a little bit more than 100 million, so which is a pretty high RMSE in this case. I remember that the RMSE has the same unit as the observation. Here in this case, the observation is a population, the population of China in hundreds. In millions, in a population of expressed in millions of inhabitants. So in this case, it means that our error is about 100 millions of inhabitants, which is pretty high. But if you compare it to the average population, then it's not that high. It's an error of a little bit about 10%. One way that you can look at this is to calculate the RRMSE. The RRMSE is the relative root mean square error, which would be the mean square error divided by the mean of the value. So in this case, we take the average of the population of China and we divide the error that we are making by the average population of China. So this is going to give us a percentage error, which in this case is 0.10, which means that we are making an error of about 10% when this model is predicting the population of China. In this case, we won't be able to have a much lower error than that because there is a lot of noise in the data that we have here. So at some point, we cannot get a model that becomes more accurate than the intrinsic noise of the data. But nevertheless, we can still do a little bit better than that. So now what we're going to do is to see if we can have more accurate result by now assuming that we have a nonlinear hypothesis. That is to say, a hypothesis that is not simply a linear relationship. We are going to look at whether we can increase the accuracy of the model by assuming a second order polynomial or a third order polynomial. So we are going to move from linear regression to polynomial regression. So now we are going to test a little bit more complex hypothesis for the model by moving to polynomial regression. So for example, we are going to assume to start with a second order where you have an hypothesis that looks like a times x to the power 2 plus b times x plus c. So we are going to assume a hypothesis that looks like this, a second order hypothesis, and we are going to see if we use now a nonlinear model that include a square term, how much more accurate can it become? So for this, we can just do the same. So we can just reuse pretty much the same thing. So we are going to say that, okay, we are going to start by using the polyfit function. We are going to fit y as a function of x, but this time we are going to use a second order polynomial. We are going to use the predicted value, and basically we are going to redo this entire thing. So we are going to use the variable p where you have the coefficient. This time p will now give us 3 coefficient, not just a and b, because now if you do a second order polynomial regression, you will get the first element of the vector p will be the coefficient a that is associated to the second order term x squared. Then we will get the coefficient b, and then we will get the coefficient c, which is just the intercept or the bias of the model. We are going to use the polyval function to mix to calculate for all the features y what is what the model is predicting, and we are going to store those predictions into the ypred variable, the ypred vector, column vector. We are going to plot the raw data and compare it with the prediction from the model. And again, we're going to recalculate the RMSE and the RRMSE. So let's see what we get. So we see that now we fit the data with a second order polynomial. So now we have some nonlinear variation. So that is to say that now our model is able to capture the fact that the growth of the population of China is still positive, it's still growing, but it's slightly slowing down over time, which we would not have been able to capture this thing by having simply a linear regression model. So now we have a model that looks a little bit better, more accurate. So one way to quantify this is to look at the RMSE, and indeed the RMSE has slightly decreased. So now it's about 107, which is now a little bit less than 10% error. Again, we won't be able to do much better than that in this case because we have a lot of noise in the data. But nevertheless, we see a clear improvement in the model, which means that in this case, going from a linear model to a quadratic model seems like it's increasing the accuracy. It makes the model more realistic. It can capture a more realistic relationship between the features x and the observation y. So here you can see that Matlab is giving us an error message here, or at least a warning. It's telling us that the polynomial model is badly conditioned. Here, this warning comes from the fact that now your polynomial model is using two features. It's using x and x squared. So here we are using a polynomial degree of order 2, where we have x and x squared. But remember that in the case of regression, when you do polynomial regression, it's exactly the same as just a regular regression. Matlab doesn't know that that the x squared is going to be the square of x. It actually considers that x and x squared are two different features, and those are just two features that are going to be used as input to try to predict the output. The problem if you do this is that those features have a very different range of values. For example, if you look at the variable x, x contains the year, so it's a variable that goes between 1960 and 2018. If you look at the average value of x, it's 1989. But now when you look at x squared, the variable x squared, it's a variable that is much larger because it's the square of the year. So now when you look at the mean of x squared, the average value of x squared is much larger than the average value of x. And that's an issue because now you have two features, x and x squared, and they have very different range, very different average value. And this is typically not a good thing in linear regression, and it's not a good thing in almost all machine learning models. It's not a good thing to have a feature that is much larger than the others because it deforms the feature space. You have one dimension that is much more elongated than the other directions, and that makes it much harder to optimize the model because the model is too elongated, so it becomes harder for the steepest gradient descent in order to optimize the model because it's so much more elongated than in other dimensions. So it makes the optimization very poorly efficient. So one way that we can overcome this limitation, and something that we will try to always do in practice, especially when it's a case like this where you have some features that are much larger than others, is that we will need to normalize the features. So for this, what we will do is just to do a simple renormalization of the features so that they have all the same range. And once we do this, it's going to make it much easier for the model to be optimized. So that's the next step that we will do. So now we will do feature normalizations. So this again, this is mostly intended to make it easier for the model to be optimized. And for this way, what we want to avoid is that some features are much larger than others. So here the problem is mostly x. So if we plot a histogram of x as a reminder, so let's look at the histogram with the possible values of x. So the x ranges between 1960 and 2020. If we look at the values of x squared, now it ranges between 3 million to 4 million, so much larger. So one thing we can do to avoid this is to do a normalization. So there is different ways that you can normalize the data. The goal of this normalization is to make sure that all the data have roughly the same scale, roughly the same range of values. So one way that you can normalize the data is, for example, we're going to take the values of x. The first thing that we are going to do is to remove the average value of x. So if we take x and we remove its average value, so now if you do this, then it means that the data will be centered around 0. So just to take a look at what I mean by that. So you started by x, the values of x that goes between 1960 and 2020. Now we are going to create a new normalized version of this feature. We're going to call it x norm as a normalized. And now if we look at the histogram of this x norm, it's going to be like the data will now be centered around 0. So now if you look at this x norm, it's just ranging from -40 to +40. It's because we have taken all the years one by one, and we have removed the average year, which in this case the average year was 1989. So now we have some data, some features that are centered around 0. So this is good, but it's not enough, because the range of the data is still not going to be the same. Like if you do the same normalization for x squared, like now if we take the square of this thing, it is also the range is going to be between 0 and 1000. So it's still a very large range as a function of with respect to x. So what we can do to do this is, in addition of removing the mean, we can divide by the standard deviation. So we're going to divide x by its standard deviation. So we're going to take x, remove its average. For all the values of x, we remove the average, and then we divide by the standard deviation of x. So if we do this, and if we look at the distribution that we get, now we get a distribution that roughly goes between -2 to +2. This is now a distribution that is centered around 0, which is good, and it goes between roughly -2 and +2. So if we try to have a little bit more fine representation of this histogram, now you have something that is mostly going from -1 to +1, just a little bit low before -1, and goes a little bit after +1. So if you do this to all the features now, all the features will be normalized. All the features will be centered around 0, and all the features will roughly have the same range of variation. They will, because you divide by the standard deviation. So the standard deviation is already capturing the range of values for each of those features. So if you divide by the standard deviation, now all those features will be kind of have the same range of values. So it's always a good thing to do this so as to have all the values having roughly the same range of values. Another way that you can do this normalization, which is an alternative way, is to do the min-max normalization. So what you are going to do in this case is to define a new normalized features where you are going to take all the values of x, and the first thing that you are going to do is to remove this time the minimum values of x. So if you do this, you take all the values of x and you remove the minimum. It means that now you will get a feature that starts at 0 and ends at 60, which is the difference that we have. Like, this is the range of years that we have. We start at 1960 up to almost 2020, so we have a range of 60 years. So if we take all the years and remove the minimum value of the year, now we have a features that goes between 0 and 60. And what we can do in order for all the features to have the same range and to go between 0 and 1, we can divide by the range of the data. So the range of the data, the way we can have it is to take the maximum values of x minus the minimum values of x. So if we do this, max of x minus the mean of x, this is going to give us the range of the data, the difference between the maximum and the minimum value. And if we do this, now we are going to get a feature that goes between 0 and 1. In this case, this is the normalization that we are going to use, because in this case we are using polynomial regression. So if x is between 0 and 1, then x2 is also going to be between 0 and 1, x3 is also going to be 0 and 1. So we will have in this case all the features that have exactly the same range, or a range that is very comparable. So it's going to make it easier to do polynomial regression while having all the features having a comparable range, which will make it easier to optimize the model. So now let's redo the polynomial regression, but now this time using the normalized feature, just to see whether we still get the warning message from Matlab. So we are still going to do the polynomial regression, but this time with the normalized feature. So let's see. So we are going to just pretty much redo the same thing. So we are going to start with the polyfit. The only difference is that now when we do the polyfit, before we fitted how to go from x to y, and this time we are, rather than using x, we are going to use the normalized version of x. We are going to train a model that does not map directly x into y. We are going to train a model that can map the normalized version of x into y. We are going to train a model that can transform the normalized version of x rather than x directly into y. But it's not a problem to have this, because it's very easy using this transformation. It's easy to transform x into its normalized value, or to do the opposite observation, to just transform the normalized version of x into the original values of x. So let's do this. So we are going to this time map the values of x, which is the normalized value. So we are going to use as a feature the normalized values of x, and we are going to map it to y. And this time we are always we are going to do it again with a degree 2. So this is going to give us a vector p which contains the coefficients. So we are going to see what is the prediction from the model by using the polyval function, and see. So here in this case, now our model can only map the normalized version of x into y. So now if we want to see what is the prediction of the model, we cannot feed the model with the variable x directly. We need to feed it with the normalized version of x. Otherwise, the model now doesn't know how to convert x into y. It doesn't know how to convert the year into the population of China. It only knows how to convert the normalized version of the year into the population of China. So we need to feed this model with the normalized version of x. So this is going to give us the predicted value, and same thing, we can just plot what the model is telling us and see the error of the model, just to make sure that everything is working well. So we can see that this time we don't get any warning message from Matlab anymore, because now it's satisfied that the features x and the features xy are both having the same range. You can see that the result that you get is pretty much the same that the one we got before. It doesn't change anything. You are just normalizing the features. But the training of the model otherwise is going to be exactly the same, but except that now, rather than mapping x to y, you are mapping the normalized version of x, but it doesn't change anything in the training of the model. Okay, so now that we see that the model, we get a better accuracy by having a second order polynomial. Now the question is, could we do better by increasing the polynomial degree even more? Like, could we do better by having a degree 3, a degree 4, etc.? So here, the only thing that we need to do is to change this factor 2. So if we want to now train a third order polynomial, we can do this. So just as a reminder, we started for a second degree polynomial, we have an RMSE of 107 millions of years. So now if we do it with a third order polynomial, we see that the RMSE is slightly lower. So a third order polynomial is a little bit better at interpolating the data. If we look at this prediction from our model, now that we use a third order polynomial, we see like that the function becomes cubic, so it's not simply quadratic anymore, so it's a little bit more complex function. It still looks like it's doing a decent job at fitting the data, but it's already starting to look a little bit suspicious, because it's predicting that the population is kind of plateauing already, which is not very realistic. It looks like the population is still growing. So let's see what we will get with a degree 4. So if we do a degree 4, it starts, so the first thing we see is that the RMSE is again a little bit lower. So the degree 4 is a little bit better at interpolating the data. The error is still decreasing, but it's doing some other suspicious thing, because it's predicting that the population would have actually slightly decreased after 1960, which is not obvious from the data. And then it has this kind of weird inflection point, which again kind of suggests that at this point the model is starting to be overfitted. We started with a model degree 1 that was quite clearly underfitted because the error is pretty high, but when we move to degree 4 like this, it starts to be to look like it's overfitted. So let's see what we get with for example a degree 6. So again, you start to have more and more variance in the model. The degree of overfitting is increasing, so you have a model that becomes more and more distorted, that will try to be distorted as much as possible in order to fit as closely as possible to the data. Let's start with a degree 10. So degree 10, we start to see like a very a model that does a lot of zigzag in order to try to decrease the error, but the error is a little bit lower. Now it's below 100. The RMSE is below 100. And let's go with a degree 20, and now you can see that the model is starting to look very weird, like it's predicting those oscillation. And if you look carefully, those oscillation, it's actually the model trying to go through every single point, like it's trying to be deformed as much as possible in order to go through every single point as much as it can. So this is a good example here of an overfitted model that really tries too hard to fit to go through every single points. And in this case, the problem is that you cannot use this model to make any prediction because it's not capturing the trend of the data, it's capturing the noise of the data. So we are going to go back to a degree 2 like this. So now the question is between degree 1, degree 2, degree 3 is which one is the best? Because it looks like if we are just increasing the degree, we can see with our eyes that it's actually becoming overfitted, but it's not clear on how to if the best degree is degree 2 or degree 3 or degree 1, because if you just increase the degree, it looks like the RMSE is becoming smaller. So the question is, when should we stop? What is the best degree to use here? And we cannot directly only use the RMSE that we find here, because it looks like the more you increase the degree, the lower becomes the RMSE. So it looks like the model is becoming better and better, but when you look at it with your eyes, you can see that it's actually becoming quite weird, and it's not actually becoming better. So the first thing we can do is to more systematically vary the complexity of the model. So what we are going to do here is now, rather than trying manually each degree one by one, we can do a loop on the degree in order to look at the effect of the complexity of the model. So let's see what we get. So here now what we are going to do is to do a loop over different degrees and to track the evolution of the RMSE as a function of the degree. So we can start by selecting the maximum degree that we are willing to use. So let's say, for example, that we are going to go up to a degree 20. And now what we are going to do is to do a loop over the degree. So we are going to do a loop, like for example, variable I going from 1 to the maximum degree that we have defined, so which in this case is degree 20. For each of those degree, we are going to do to use the polyfit function. So we are going to use to conduct a polynomial regression of degree I, where we are going to use as feature the normalized values of x. We are going to map it to the observation y, and we are going to do this with a degree I, and it's going to do this for degree 1, degree 2, degree 3, etc. By the way, we didn't look at what we get with degree 0, just for fun. We can do it for degree 0 here. If you do degree 0 is just a constant term, so it's just gonna give you a constant prediction, which in this case is just going to be the average of the observation y. So not very interesting because it doesn't predict anything. So we don't need to consider this case. We are going to start with just the degree 1 directly. We are going to exclude the degree 0 case. So now for each of those models, we are going to calculate the value that is predicted from this model by using the polyval function, where you use the coefficient p that has been determined by the model, and you look at what the model is predicting for the normalized values of the feature, and we are going to calculate the RMSE. So This time I'm going to call it error, and I'm going to calculate this error for each individual degree I. So I'm going to construct a vector of error where each element of this vector will correspond to the error for a different polynomial degree. So I'm going to reuse exactly the same function here, which gives me the RMSE. So I'm still going to calculate the square difference between the predicted and the true value of y, put it to the square, take the average, and take the square root. So this is going to give me a vector that contains the error for each polynomial degree. And then the last thing is I will want to plot the error as a function of the degree. So I will want to put for each degree going between 1 to the maximum degree, I want to plot the error, the evolution of the error. So let's see what we get with this. So we can see here that, so here I have on the y-axis, I have the RMSE of the model, and on the x-axis, this is the degree. Here what we can see is that the RMSE is just decreasing fairly monotonically as a function of the degree, which means that the more complex the model becomes, the better it is at interpolating the data, and the error is just decreasing. So this doesn't really make it possible to select the optimal degree that we should use for this model. And this is why when you do machine learning, you cannot only train the model based on the entire training set, because in this case, the more complex model is always going to be the best at interpolating the data. What we need to do is to test the ability of the model to generalize, to make some prediction for new unknown data. And for this, the trick that we can use for this is to split the training set. We can split the assets into a training set that we will use to train the model and a validation set that we will use to evaluate the model, evaluate the ability of the model to make some good prediction for unknown data. So we are going to keep a fraction of the data points that we are going to keep invisible to the model. We are not going to use those data to train the model, and we are going to keep those data until the very end in order to see how well the model is generalizing, how well the model make accurate prediction for data that are far away, for data that are not included in the training set, that we are not used to train the model. So for this, so we are going to now split the data set into a training and validation set, and this is gonna be useful to test the ability of the model to make some good generalization to unknown data. So one way you can do this, there's different way you can do this in Matlab, but one way you can do is to first select the fraction of the data that you want to use for the training. So here we have very few points, 59 data points. So for this, we need to use a pretty big validation set. Otherwise, if the validation set is too small, it won't be enough to really test the accuracy of the model, the ability of the model to generalize well. If you have a larger data set, a data set that is made of millions of data points, then you can afford to use a smaller validation set, because since you have so many points, then the validation set will already be large enough, even if you are using a limited fraction. So typically for the validation set, we typically use 30% or 20% of the data point. But here, since the data set is so small, we are going to use 50% of the data for the training of the model and 50% of the data for the validation of the model. The reason we do this is to make sure that we keep enough, a number of data that is large enough in the validation set to really check the ability of the model to generalize well outside of the data it was trained on. The reason that we do this is that we want to have a model that we can trust, a model that we can use to make some extrapolation and to predict what the population of China will be in 100 years from now. For example, if we have a model that is not so trustable, if it's a model that we are not fully sure how well it can really generalize to new data points, then we won't be able to use this model to make some very robust prediction for the future. So in this case, we will favor the ability to generalize will be our priority. So we will make sure that we use a validation set that is large enough. So we are going to use 50%. So P is 50% here. It's the fraction of the data in the training set, which is also going to be 50% is also going to be, as a result, the fraction of the data that will go in the validation set. So now that we have this, one trick that we can use to now what we need to do is to randomly separate the data into training and validation sets. So we start with 59 data points within the data set. Now we need to randomly pick some data to put within the training set and to put the rest of the data into the validation set. So one way that we can do this is to start with the vector of the feature. So vector x, for example, if you look at the vector x, it has 59 components, 1, 2, 3, 4, 5, and up to 59. One way that we can shuffle this vector is to generate some random integer. If we generate some integer that goes between 1 to 59 and we put those integer into a random order, then we can say that we can reshuffle the variable x, and then we will be able to take the beginning of x and to use it for the training set, and to then take the end of the variable x and to use it in the validation set. We need necessarily to shuffle the vector x first, because if we don't shuffle x, then we would always use the early years, like 1960, 1961, 1962 to do the training, and we will always use the recent years, 2010, 2011, 2012 for the validation, which would not be fair. We need to randomly split the data into training set and validation set. We cannot use the beginning only for the training or the end only for the validation, because in this case the data are very well ordered by increasing year. So we need to shuffle the vector x, and one way we can do this is to generate a list of integer that goes between 0 and 59. So in this case, so we have the variable m is equal to 59. That's the number of component that we want to generate. So here we are going to use the function random perm. So what this function does is that it will generate a 59 integer number, 1, 2, 3, 4, 5 up to 59, and then it's going to perform some random permutation, so that it's going to put those integer into a random order. So it takes as argument just the number of integer that needs to be shuffled. And so if we do this, now it creates in the vector idx, what it does is that it creates a column vector that contains all those 59 integers. So here we have 1, we have 2, etc. And like all those, we still have all those integer are unique. There is no integer that is 2 times the same one, but they are now just in a random order, not 1, 2, 3, 4, 5 up to 59, but now in a random order. And we can use this to shuffle x. So now what we are going to say is that based on this, we can define the x values for the training set. And for this, what we are going to do is we can say that we are going to use the normalized values of x, and rather than taking all the values of x, so here we would take all the possible values of x, now we are going to take them between only over a certain range. So we are going to take those values between the beginning and up to the end of the training set. So in this case, the end of the training set depends on the size of the training set that we want. So we want to have 50% of the data points. We know that we have m points, which is 59. So if we want to know where we should stop, the one way to do this is to use the command round and to multiply the number of points m times the fraction of the point that we want to use. Here in this case, if we take the product of the number of point m times the fraction of the points that we want to use in the training set, it's going to tell us that 30 is the number of points that we need to include in the training set. So we need to use the command round here in order to get an integer number, because if we just take m times p, it gives us a real number. So in this case, we need to have an integer number to say that we are going to use element 1, 2, 3, 4, 5 up to 30, and this is what we are going to put in the training set. So we are going to write it like this. We are going to say that we are going to use all the elements from 1 to up to 30, and we are going to select those values and to put it into the training set. But again, if we do this, we are going to necessarily select only the first years. So we start with if you look at the variable x norm, it starts at 0 and then gradually increase. So now if we take the beginning of x norm between 0 and 30, if we do this, then we are going to select only the beginning, 0, 0, 0, 1, 0, 0, 3. So this is not good because we would be only selecting the beginning of the years. So what we need to do here is to shuffle the input x. So rather than using x norm like this, we are going to shuffle those data. Here they are still ordered by order of increasing years. So to shuffle the data, we are going to say that we are going to take those variable x, and we are going to reorder them with the new index that we are just created. So if we do this, now it's going to use those new index, which are not 1, 2, 3, 4, 5, but now those integers are in random order, and that's going to dictate what will be the new ordering of the component inside the vector x norm. So now if we look at this vector, now it's just in random order. There is no clear ordering of the data anymore. So that's what we are going to use in order to define the training set. We are going to first select the number of points that we want, going from 1 to 30. Then we are going to put this into the index that we just created in order to shuffle those data, and we are going to select those data into the feature x norm, and this is going to randomly select 50% of the normalized feature x norm and put them into the training set. We are going to do the same now to create the validation set. So we are going to create a vector x val. We are going to first select the range of the data that we want. So now we want the remaining of the data. So we want to restart from 30. That is to say, in this case, we used the value 30 as the last element to put in the training set. So we are going to restart at 31. So this value plus 1, and we are going to go until the end the vector, where the end here is going to be just the value m, that is to say 59. We are going to take all those elements and shuffle them with the new index vector that we just created, and we are going to take this to pick those points from the normalized feature xnorm. So once we do this, what we have now is we have created two new variables. So we started with only xnorm, and we randomly picked its number. We created two new vector xtrain and xval, which contained exactly the same values at xnorm, but just 50% of those xnorm values are now in xtrain, and 50% of those xnorm values are now in the xval, the validation set. So now we have two vectors. Rather than having only xnorm, we have xtrain that contains 30 data points and xval that contains 29 data points, and this is just a random combination of the starting feature vector xnorm. We need to do the same for the observation vector for y. We need to take the same corresponding values for each xtrain values. We need to know its corresponding observation. This is so that we can train the model. So we are going to do exactly the same. We are going to use exactly the same vector idx, so that we are sure that we are picking every time for a couple of training examples. For each value of x, we need to pick the same corresponding values of y and put it in the training set. And for each values of x that we picked and put in the validation set, we need to also put the corresponding values of y in the validation set as well. So we need to basically do exactly the same, but for y. So now we are going to select exactly the same points from, this time, the feature variable y, and to put 50% of those features into the training set, and to put 50% of those features into the validation set. So this is now, just to see what it looks like, we can just plot this thing. So for example, if we just start with the entire data set x and y. So if we plot this, we have the entire training set. Now if we want to put like, this is the entire data set. So now if we want to only plot the training set, I'm going to plot only y train as a function of x train. So it's going to do it like this. And if I want to also plot the validation set, so I'm going to hold on to put those two things on top of each other. So now I'm going to plot on the same plot the validation set, so yval as a function of xval with a different symbol. And so now let's see what we get. So here now we have a plot where we see in blue this is the training set, and in red this is the validation set. So we have randomly split the initial data set into roughly 50% belonging to the training set and 50% belonging to the validation set. And here, if you do this several times, you see that this splitting is not going to be always the same. It's going to randomly split the data sets into training and validation set, and every time you refresh it, it will do a different splitting of the data. So this is going to be randomly changing every time you run your script, unless you fix the seed of the random number generator so that you always get the same random number. Otherwise, if you don't fix the seed, then you will get a different split of the data into training and validation set every time that you rerun this script. So now let's see what it changes now that we have split the data set into training and validation set. How does it change the training of the regression model, and what should we use to do the training, and what should we use to do the validation? So now what we are going to do is to retrain a quadratic model, but this time with the train validation, the training validation split. Okay, so let's do this. So we are going to redo exactly the same thing. So we are going to restart by using the polyfit function. So now we need to think carefully about what do we use for the training. Remember that now the reason that we split the data into training and validation set, this is so that we can train the model based only on the training set, and later on we can validate the model based on the validation set. So here we should not and won't and will not train the data based on the entire training set, because that would be cheating if we do this. We cannot evaluate the model based on the same data that we used to train it. So now we're going to train the model using polyfit only based on the training set. So we are going to teach the model how to map x into y, but the only training example that we are going to provide to the model is only the features x and the observation y that belongs to the training set, and we are going to exclude the data corresponding to the validation set. And here we are going to use a quadratic model, so we put the degree to be 2. And so now there's two things that we can do. We can see how well the model is interpolating those data. So we can see how well is the model interpolating the training set. And the other thing is we can see how well the model is predicting the validation set. The validation set are some data that the model has never seen yet. So we can test how well is the model doing in predicting those unknown data belonging to the validation set. So one way that we can, one thing that we can use for this is to calculate first the values that are predicted by the model for the training set. So this is going to allow us to test the accuracy of the model on the training set to see how well does it interpolate the training set. So for this we are going to use the polyval function. So we're going to see for the coefficient p that we found, we want to see what the model is predicting for the training set. So here we are going to put as argument the training set, and this what this function is going to tell us is for each of the point of the training set, it's going to tell us what the model is predicting, and this is going to allow us to find how accurate is the model at interpolating the training set. But now we are also going to do the same thing to see how well is the model predicting the validation set. So now we are going to define a different vector variable that will now contain the prediction of the model when we are trying to predict the observation that are predicted for the validation sets. So now we are going to pass to this function the feature value that corresponds to the validation set, and we are going to see what the model is predicting. So this model has never seen those validation those features belonging to the validation set. It has never seen those training example. So we are going to see how well does it predict this validation set. So let's see what it looks like. So let's plot first the training set. So if we do this, we're going to first plot the training set. Then let's add to this the validation set in a different color. So we're going to use the validation set, and let's now add the how well the prediction of the model for the training set. So if we take the training set, so we're going to plot the prediction of the model y train as a function of x train, and see what the model is predicting. So let's do this. So now it's become a little bit harder to see, because now the values have been shuffled. So like it's not showing a very nice line anymore. So let's see if we plot this. So let's put all the values for the training and validation set as crosses, and let's see as a small circle like this the prediction from the model. So it's a little bit hard to see, but you can see that the model is making some prediction that, oh sorry, I'm plotting 2 times the same thing here. So I'm going to plot as a function of x train. I want to plot the predicted value, not the training set value. So I want to plot as a function of the features value belonging to a training set. I want to plot the prediction from the model, which is y pred train. So let's see what we get. So okay, so it's a little bit easier to see. So this is in yellow here, this is the prediction from the model for the training set. And if we look at this for the validation set, so yeah, so I need to plot it as a function of xval, and how does it map to yval. So let's see what it gets. So now we have the model like this, which is again making a pretty decent prediction. So let's plot everything all together just to have all the information. So we're going to plot, so as crosses, the training set and the validation set in 2 different colors, and then we are going to put the values that are predicted for the training set by the model and the values that are predicted for the validation set as small circles. And I did the same mistake again. So okay, let's do this. Okay, so now we have, obviously the model doesn't change for the training and the validation set. Like the model is still the same, but sometimes you interrogate this model for the training set. Sometimes you interrogate it for the validation set. The model remains the same. It's the same function. It's the same quadratic function. And you see it's interpolating pretty well the training set that you have. If we try to do this for a higher degree, let's see what we would get. So this is what it would predict. So it would try to interpolate as much as it can the training set here in orange, and it would try to predict some values for the validation set. But as I can see here in violet, the prediction for the validation set do not necessarily seem very good. So we need to look at this a little bit more accurately to now again systematically change the polynomial degree and look at how well is the training set interpolated, and how well is the validation set predicted. And that way we will be able now to select the optimal degree for the model. So let's go back to a degree 2 here, and then so let's now redo the same thing that we did before. So we are going to now do to look at the effect of model complexity on underfitting and overfitting. We're going to see how well if we can characterize the degree of underfitting and overfitting of the model as a function of its complexity. So so we are going to to start with, again, we are going to say that we pick 50% of the data that we are going to use in the training set. We are going to say that the maximum degree that we are going to use, for example, is 10. So we are going to check degree 1, 2, 3, 4, 5 up to 10, and we are going to start to do a loop on the degree. So for I equal 1 to the max degree that we have here, which is 10, we are going to look at, for each of those degree, we are going to test what the model is predicting. So let's first redefine the training set and the validation set. So let's retake it from there. Okay, so it's recalculating the training set and the validation set randomly. So we are going to do the loop on all the degrees. So we are going to say that we are going to calculate the coefficient predicted by polyfit, where we try to map the training set to the values of the observation for the training set. And we are going to assume for the hypothesis a degree I, where I is going to change 1, 2, 3, 4, 5 up to 10. Now we are going to see how well is the model predicting, interpolating the training set. So we're going to calculate the values of the observation Y that are predicted for the training set by using the polyval command, where we're going to use the variable p that we just obtained by training the model, and we are going to interrogate what the model is predicting for the values of the training set. We are going to do the same to look at how well the model is generalizing by looking at what it is predicting for the validation set. By using polyval again, by looking at what based on those coefficient p, what the model is predicting for the validation set. So now we have those two variables that can tell us what the model is predicting for the training set and the validation set. So we can calculate the error for the training set and also the error for the validation set. So I'm going to define the error for the training set, and I'm going to store it as a function of I. So for each degree I, I'm going to store this error. And so I'm going to reuse the same function. The error, I can get it this time. If I want the error for the training set only, I need to compare the values that are predicted for the training set to the real value of the feature inside the training set. So Y train, I need to take the square difference of this thing. Then I need to take the mean of the square difference. And if I want the RMSE, I can take the square root of this. This is gonna give me the RMSE of the training set. I can do the same to get the RMSE of the validation sets to see how well is the model doing in order to predict the values for the validation set. So now if I want to do this, I need to compare the values that are predicted by the model for the validation set with the real values, the real observation for the validation set. And this is going to give me the error for the validation set. And once I have this, then I will just be able to plot on the same plot the error that I get for the training set and the error that I get for the validation set. So I want to plot for each of the degree. I want to plot the error for training, and I want to plot on the same plot, I want to plot the error for the validation set. So I am going to do it like this. I'm going to plot for each of the degree going from 1 to the max degree. I'm going to plot the error for the validation set, and I'm going to hold off. Okay, so let's see what we get with all of this. Okay, so we get some pretty weird results, but nevertheless not fully unexpected. So in blue here, what we have in blue, this is the training set error. So this is the error that the model is making when predicting the training set. And here, as you can see, here is the same result as before. The error becomes lower and lower as you increase the polynomial degree. The more the model becomes complex, the more you use a high degree, the lower the error becomes. It's because like the model becomes very complex, so it can be very deformed so as to interpolate as well as possible the values into the training set. So in general, when you use a higher complexity, a higher polynomial degree, the error for the training set is always becoming smaller and smaller. However, we see that for the validation set in orange, it's a very different trend. Initially, the error of the validation set is pretty high. Then it looks like it's reaching a minimum, and then it's increasing again. The fact that the validation set error is increasing at high degree means that when you go to a high degree, very complex model, the model does not generalize very well. The model starts to have a high variance. It becomes so complicated that it tries to oscillate like crazy and will not make accurate prediction. We can see that the prediction for the validation set values, the values that were not used to train the model, is actually becoming worse and worse as you increase the degree of the model. So here there's several things that are less expected. The first thing is that at the beginning we see that the error for the validation set is lower than the error for the training set, which is very unexpected because you train the model based on the training set, so it should be very good at interpolating the training set. But here we find that the model is actually better at predicting the validation set than at predicting the training set, which is not really what we were expecting. And this is a good example of the fact that this is the kind of result that you can get if you choose only one validation set and one training set. Because if you do this, it's possible that you might be very lucky or very unlucky, and that you will pick specifically one validation set that is actually very easy for the model to predict. And in this case, it's probably a validation set that is pretty easy for the model to predict because the error for the validation set is actually smaller than the error for the training set. But sometimes you can pick a validation set that is like very challenging to predict, and you would find some results that also do not make sense. So this is a good example that if you just randomly pick one fixed validation set, you cannot necessarily make very accurate prediction. And actually, if you repeat this thing several times, you will get different results. Like every time you repeat it, it's going to change, make a different split between the validation and the training set. So every time you repeat it, you will get different values. We always see that it's roughly the same trend, like the error for the training set is decreasing as the model becomes more and more complex. And for the validation set, there is always some kind of minimum between 2 and 4, and then it increases. So the trend remain the same, but the value that you will get, they will depend quite a bit, and you can get a different result. So this doesn't make it a very the fact that those number changes so much every time you repeat this simulation make it like non-ideal. Like it's not ideal to choose what is the optimal degree that we should use, because we get a different answer every time we restart this calculation. So this is where it would be good to use the cross-validation method, because you would use a combination of different split of test set and validation set, and that would allow you to have a more accurate prediction, because you are not relying on only one fixed validation set, but actually you are splitting your training set into different you are splitting your data set into different folds, and every time you will be training your model based on a given number of those folds and validating based on the remaining fold, and then you are going to iterate like this by picking every time a different fold for the validation. So you will get a more average response of the model that will make the result more accurate and more statistically significant. So here in this case, this is not what we are going to use. Like you will have to use to code the cross-validation in your homework. Here, what we are going to use is another method that can be used, which is to just repeat this a high number of times. One way that you can try to average out those results and have some results that are a little bit more statistically significant is to repeat this regression a pretty high number of times, where every time you split the data set into different combination of training sets and validation sets. So every time you will get a different result, and then you will take the average of the RMSE of the model, average over the different repetition, average over the different split of training and validation set. And by taking this average over several repetition, then it's going to allow you to have some more clean result that will allow you to pick more confidently the best degree that we should use for this model. So we're going to do this by having now we're going to do some iterations on different training test splits. So we're going to redo exactly the same. So I'm going to retake this code here, but this time I'm going to add an additional loop to say that I'm going to do this entire thing a given number of times. So I'm going to take this entire block where it's first splitting the data into training set and validation set, and then making a loop on the degree, calculating the training error and the validation, and I'm going to repeat this entire block a certain number of times to have more statistically significant averages. I'm going to calculate the average error that I get for the training set and the average error that I get for the validation set over several repetitions. So I'm going to define the number of repetition that I want. I want, for example, let's start with 100 repetition. I'm going to split to test 100 different splits of training and test and validation set, and I'm going to define my error of training and error of validation, and I'm going to say that those errors are initially 0. So I'm going to say that those are initially some 0 vector. I need to define the size of those vectors. So those vectors, you will have a different value for the training error for different degree. So the size of the vector will be the maximum number of degree, and you have only one column. And I'm going to do the same thing for the validation set. Here, the reason I need to say that those variables are initially 0 is that I'm going to do a loop on different repetition, and every time for each repetition I'm going to increment the value of the error, and then at the end I'm going to divide all those errors by the number of iterations. So I need to make sure that those variables are initially 0, And then for each repetition, I'm going to increment those error by the error that I get on each of the repetition. And then I'm going to divide by the number of repetition in order to get the average value of those error. So now I'm going to start the loop. So I'm going to start to do a loop on the number of repetition. So from 1 going to the number of repetition, I'm going to do the loop on this entire thing. So initially I'm going to start with doing the random training and validation split, and every time for each iteration is going to split those values in a different way. Then I'm going to do the loop on the polynomial degree to test what is the error. For this particular split, I'm going to test the different degrees, and here every time for a given degree, what I'm going to do is to increment the error. So rather than just saving the error like this, I'm going to increment it. So I'm going to say that the error is the former error plus the new error that I get for this degree, and add this to the values of the error. And I'm going to do the same for the validation error. I'm going to just increment it like this. Then I'm going to end the loop on all the repetition, and at the end I'm going to just take the error for the training and divide it by the number of repetitions. I'm going to take this vector. This vector contains the error of training for each of the degrees, and I'm going to divide it by the number of repetitions so that I can get an average value of the error, average over all those 100 repetitions. And I'm going to do the same for the error associated with the validation set. I'm going to take all the validation set error divided by the number of repeats in order to get the average value of the error. And again, I'm going to plot the training error and the validation error as a function of the polynomial degree. Okay, so let's see what we get using this. So it's a little bit slower because now it needs to perform a high number of those fits. So this is what we get. So now we get a much smoother response. Like we see that the training set in blue is just smoothly decreasing. So the higher the degree, the more accurate the model becomes at interpolating the training set. And when you look at the validation set, initially it is slightly showing a minimum, or at least slightly pretty flat, and then at some point it starts to increase. So when you are at degree 5 and higher, this is where the model becomes severely overfitted, that is to say that it doesn't generalize very well. It makes a big error when trying to predict the feature value for the validation set. So now we can look at we can clearly see the different domains for this model. When the degree is very low, like degree 1, the training set error is pretty high. So it means that in this case, the model is most likely slightly underfitted. Not that much, but slightly underfitted. When you increase the degree, you will probably have an optimal values somewhere around 2 or 3. And then as you continue to increase the degree, then you see a signature of overfitting, because you see that the model becomes interpolate very closely the data in the training set. So it starts to fit the noise of the training set, but does not manage to properly generalize it. It makes a big error at predicting values for the validation set. So it means that if we select a degree that is too high, the model will look pretty accurate because it will fit the data pretty well, but it actually will be very, very bad in practice because its prediction to new unknown values will be pretty bad. So now if we want to more accurately select what is the best polynomial, like one way we can do this is first we can focus a little bit more rather than looking at every single degree between the 1 and 10, we can look at between 1 and 6, because like the error becomes so large after 6 that we can't really see much, like it's kind of making those errors look flat. And then the last thing is that we can look at what is the polynomial degree for which the error for the validation set is minimum. So that's going to be the criterion to choose the best polynomial degree. So the optimal polynomial degree, I can look at it and look at for which degree is my model the best at interpolating unknown values that are in the validation set. So what I can do is to look at when is my model predicting a minimum value for the validation error. I need to look for which degree is the error associated to the validation set minimum, and I want to get two things out of it. I want to know the RMSE of the model at this value. So I want to know actually the value of this error, like the value of this error here when it's an optimal model. But I also want to know the degree. So I want to know the degree I, where the model is the value of the degree for which the validation error is the minimum. So I need to know those two information. M is going to be the minimum of the error value, error validation vector, and I is going to be the component, the index of the component of this vector for the component that shows the minimum value. So let's see what we get. So let's run this thing another time. So now we see a better picture. We see that when we look at in blue, the training error is just decreasing monotonically between degree 1 to degree 6. And now we have a better view of the validation error, which tells us how well the model is generalizing. And here we find that in this case, the model is predicting a minimum value for the validation error for a degree 2. A polynomial degree 2 is what the model is predicting to be the optimal degree in this case. So it's possible, like as you can see here, polynomial degree 1, 2, and 3 are not very different from each other. 1 is a little bit higher, so 2 and 3 are definitely better, but between 2 and 3 it's a little bit unclear which one is the best. Nevertheless, it looks like it's a little bit better for 2 in this case. So just a quadratic function appears to give you the best balance between underfitting and overfitting at high polynomial degree. So now based on this, we now know that the optimal value, the optimal coefficient, the optimal degree that we should use for the polynomial regression is 2. So this factor 2, the fact that we use a degree 2, this value of 2, the fact that the higher coefficient that we use in polynomial regression is 2, this is one of the parameters of the model, but to distinguish it from the real parameters of the model. The parameters of the model are the coefficient A, B, C. Those are the weights of the polynomial regression. 2 is what we call a hyperparameter. It's a parameter that characterize the type, the complexity of the model, or characterize the architecture of the model. In this case, the only hyperparameter of this model is only the maximum degree that we are considering. And here we find that the best value for this hyperparameter is to use a degree 2. So in general, for each machine learning techniques, you will always have to tune the values of some of those hyperparameters like this. And this is what the validation set is for. The validation set is specifically used in order to find the best possible values, to tune the optimal values for the hyperparameters. So, okay, so now that we have found that a value for this hyperparameter of 2, that polynomial degree 2 is the best possible value, now we can use our model to make some predictions. So now that we have optimized the hyperparameter, now we can say that, okay, now we know that we are going to use a polynomial degree 2 model, and we are going to use this model in order to make some predictions. So as a reminder, let's plot again the values that we have. This is the raw data in this case, so let's replot it again. So this is the raw data, and we want, now that we have a model that can directly map the year, the feature year, and map it to the observation, which is the population of China in millions of inhabitants. Now that we have this model, we can use it to make some predictions. So now what we are going to do is we are going to retrain this model, but now we know that the optimal values for the coefficient is 2, and we are going to use this model to make some predictions. So we are going to first retrain the model. So we are going to again use the polyfit command and say that we are going to train a model that can map the n norm into the values of y, and we are going to use, now we know, a polynomial model of degree 2. And what we are going to do now is to use this model to make some prediction for the future. So for this, now that we have this model being trained, we are going to interrogate what is the value predicted by this model for future years. So we are going to plot what the model is predicting for future values of the year. So just to look at this, we are going to predict, for example, for between the year 2020 up to the year, let's say, 2100. We want to see what the model is predicting for all those years. So we are going to define a new range of features that goes between 2020 to 2100 by increment of 1. So it's going to be 2020, 2021, 2022. And we are going to see what the model is predicting for that. Again, just remember that the model that we have trained, it doesn't know how to map the year into the population of China. What it knows is how to map the normalized version of the year into the population of China. So we need to take those X future input, and we need to normalize it in the same way that the model expects. So we're going to define a new value for those features. So X future normalize. We are going to normalize this. We need to make it clear, we need to normalize those features exactly in the same way that the model was trained. Now we should not normalize those features based on the range of those new values here, because the model has never seen this range. So we need to normalize the feature in the very same way that the model learned to deal with. So we are going to use exactly the same normalization operation so that the model knows what it is getting. So we are going to use those X future variables. we are going to remove the mean of x, which is exactly the same thing that we did. At this point, the values would start at 0, and we are going to divide it by the range. And here again, we are going to divide it by the range of the original values of x, because this is the transformation that we used to train the model. So those maximum and minimum values of x, those are not the maximum and the minimum values of x future, but we still need to do exactly the same normalization operation. So this is, in this case, the normalization, because this is how we train the model. The model should receive as an input the very same some data that have been normalized in the very same way. So now we are going to see what the model is predicting for the future. So we are going to see what is the observation that are predicted for the future by using the polyval function. We are going to see what the model is predicting for the future features that we have just defined here. Okay, so at this point now we will see what the model has calculated, and we will plot the we will plot the model. First we will plot the raw data. We are going to hold on, and then we will plot the prediction from our model. So we will plot for what the model is predicting for the future years. We'll see what the model is predicting, and we are going to hold off. Okay, so let's see what the model is predicting. So here in blue, those are the training data, and here in red, this line here is the prediction from the model. So what the model is predicting at this point is, since we trained the model to be a quadratic function, it thinks that the population of China is going to follow a quadratic function. Of course, the model is just going to follow in this case, the type of function that you've determined to be the best. So it means that here what the model is predicting is that the population of China will continue to increase, will at some point reach some kind of plateau around 2050, and then will start to decrease. So most likely this model is not very accurate, because at some point it's very unlikely that the population of China will start to decrease, but it's probably pretty accurate to predict the near future. So for example, if you plot the prediction over a more narrow range, for example, if you just see what happens during the next 10 years, then probably the model is pretty accurate. It's going to give you a prediction that is pretty accurate. Like maybe you can even go a little bit higher and predict up to 2040, and most likely the prediction from the model is going to be pretty accurate. So what the model, we can look at what the model is predicting. We can look at for the future, or we can look at what the model would be predicting if you use the polyval function. You can also interrogate this for a specific number. So you can see, for example, if I want to predict in 2040 what the population of China will be, I can just use this and see that. So here, this is a good example of the fact that the model doesn't know how to predict the relationship between the year and the population of China. It only knows how to predict the normalized version of the year to the population of China. So first we need to normalize. We cannot directly say what the model is predicting for 2040. We need to first normalize this year. So what we can do is to take 2040. We need to remove the average values of x, and then we need to again make the normalization to divide by the range of the values of x. So it would be good to have a function that can do that automatically. And what did I do? So I guess this is it. Okay, so now what the model is predicting is, so this, we can now interrogate what the model is predicting for the year 2040. And what the model is predicting is that there will be 1.158 billion inhabitants in China in 2040. And we can do that for different values of x. So the population is predicting that there would be 1.6 billion people in 2050, and then the model in this case would predict that the population would start to decrease after 2050, which is pretty unlikely. In this case, it means that at some point we cannot predict the future, or we would need more accurate data and more data if we wanted to predict the future more than 30 or 40 years in advance. So this is, in this case, an illustration of the different steps that you need to do for a machine learning model. Again, the step one would be to just load the data. You need to import the data. If you don't have any data, then you would not be able to do anything. Then it's always a good idea to just visualize the data. There's two ways you can visualize the data. The first thing you can do is to plot the relationship between the features and the observation, the relationship between input and output. You can also plot the distribution of each of the features to have an idea of their range. That's always a good idea. And then you can start exploring the data by trying different types of models. At some point, remember that you need to, if you have some features that have very different values, you need to do some feature normalization. You need to make sure that each of the features have roughly the same range. Otherwise, that would be an issue to optimize the machine learning model. And then you need to perform the regression based on the normalized features rather than the features themselves. Then the next thing is that you will need to optimize the hyperparameters. You will need to find what is the right degree of complexity, what is in this case the maximum polynomial degree. So for this, the right way to do this is to split randomly the data set into a training and a validation set, and to see what the model is predicting for the validation set, to see how well is the model interpolating the training set, but more importantly, how well does it generalize to the validation set. And then based on this, you can systematically explore what the model is predicting for different increasing complexity. And if you do this, it's going to allow you to find the optimal degree of complexity. Remember that especially when you have a small data set like this, it's always a good idea to either repeat on different training and test set splits. This is repetition on different training and validation splits. We will talk about the test set later. For now, we have only talked about the training set, which is used to train the model, and the validation set, which is used to pick the optimal values for the hyperparameters. The training set will come later. And now, so if you do this, it allows you to find the best values for the hyperparameter. But it's always a good idea to iterate on several training and validation split, because if you only do it once, then you cannot be sure that your result might very strongly depend on the choice of the validation set. So if you repeat randomly on different validation sets, or if you use the cross-validation method, then you can have more accurate estimation and have a smooth response where you can very clearly see what is the best choice for the complexity of the model. So in the best polynomial degree to use in this case. And once you have done this, then you can use your model to make some predictions. You can use your model, your trained model, to predict what will happen in the future. You can also use this to make some prediction for the past. We couldn't say we can say like what the model was predicting, for example, between 1900 and 1960, to try to see if we can guess what the population of China was in the past. So let's see what the model is predicting. And so here, so it's clearly not very accurate, because it would think that the population of China was negative before 2040, which is clearly not good. Let's see what we would get with a degree 3, just to see if it can guess. Yeah, so it's not much better. Like clearly this model in this case, just using a polynomial regression, is not good to try to predict what was the population of China in the past, because the population of China was growing exponentially. So here, if we are just using a linear model, it's going to be pretty bad at guessing this initial exponential growth for the population of China. Like one way we could do this is to assume an exponential relationship between the year and the population of China. For example, one way you could do this is by fitting the log of y, or to take the exponential of the year as a fitting parameter. That would be one way to still use polynomial regression to fit an exponential relationship between the input and the output. Nevertheless, so you can use this model to make some predictions for what happened before or after the data that have been measured. So that's one way of how you can benefit from a machine learning model once it is trained to make some prediction for the future. Of course, you can make some prediction for the near future, and typically the model will be pretty robust at doing this. But the more you want to predict far in the future, then the more inaccurate your model will become, because it's become harder and harder to make some prediction for very long in the future by relying on data from the past, because the data from the past might not be necessarily representative for the data for the future. So in the future, what we are going to see is, in this case, everything we saw is based on polynomial regression, which still assume that there is a polynomial relationship between the predicted feature and the input, so the predicted observation and the input feature. But in many cases, in machine learning datasets and models, the relationship between input and output is not linear like this, so it cannot be described easily by a polynomial model. So we need to move towards more complex model, like artificial neural network, for example, that can offer a more complex relationship between the features and the observation. And the other thing that we are going to see before this is to see the case where you have more than one feature, when you have different features. If you are trying to predict the population of China not only based on the year, but also based on other types of features, like other information that you can get from other possible descriptors that you think might be correlated to the growth of China besides the year. If you have those extra descriptors, then you can also use them as input to have a more complex model that doesn't have only one feature, only one input, but several features. So now we will need to use a multivariate regression, where you have several features, and each of those features can potentially bring something useful to predict the observation that you want to predict.